Welcome back to The Deep Dive, the show where we take complex source material, strip it down to its fundamental core, and deliver the nuggets of knowledge you need to be truly well-informed.
And today, we are strapping in for a flight into, wow, the mathematical bedrock of stability itself.
It's a big one. We're moving beyond simple probability, the chance of a single event, and we're entering the realm of mathematical certainty.
Or, maybe more accurately, the realm of powerful mathematical guarantees. The very things that allow us to trust real-world data collection, even when everything seems chaotic.
That's right. Our mission today is pretty laser focused. We're diving deep into two linked, absolutely foundational concepts. First up is Chebyshev's inequality.
Think of it as a universal safety net for randomness.
And second, we'll use that to understand the weak law of large numbers. If you've ever wondered why averaging out noise actually works, or why massive systems like insurance or, I don't know, manufacturing can reliably predict their failure rates.
Or why scientists are so obsessed with large sample sizes.
Exactly. This deep dive is your answer.
The central question we're really tackling today, maybe the philosophical question, is how we bridge that gap. The gap between theoretical probability, what should happen in a perfect world, and what we actually see.
The observed frequency from messy real-world samples, what does happen.
And we have the tool that forges that bridge.
So we're starting with Chebyshev's inequality. I think the best way to frame this is as the ultimate universal worst-case scenario analysis. It gives you the absolute maximum risk you could ever face from an outlier.
Exactly. The really extraordinary thing about Chebyshev's is that it works even when we know absolutely nothing about the underlying distribution of the data.
You know nothing about the shape.
Nothing. And that robustness is its monumental strength. But as we're going to see, that very strength is also the source of its, well, its main weakness.
And this tool, this hammer, becomes the absolute necessity to mathematically prove the weak law of large numbers.
Which is the single most important principle, proving that what you measure, your relative frequency, eventually has to converge to the true theoretical probability.
Okay, let's unpack this. We're going to show you the simple, really elegant proof behind these massive ideas and explain why they are the definition of statistical stability. All right, let's start with the central idea of this inequality. If you look at any collection of data, you've always got a central tendency.
Your expected value, the mean.
Right, the average. And then you have the outliers, the values that deviate pretty significantly from that average.
Precisely. You can visualize a probability distribution like a landscape. The mean, the expected value. That's like the center of mass.
Yeah.
Chebyshev steps in and gives us a hard number, a quantitative measure, for the risk of landing way out in the hills, far away from that center.
So, and this is key, Chebyshev doesn't tell us the exact probability of a large deviation.
No, it can't. Without knowing the precise landscape, the distribution shape, that would be impossible.
Instead, what it delivers is an upper bound. It's basically saying, look, I don't know the exact risk, but I can guarantee you, I can promise that the probability of landing way out here beyond this line can absolutely not be greater than this specific number.
It's a universally guaranteed ceiling on your risk. Hashtag 1.1 defining the universal upper bound. And that ceiling is formalized in the inequality itself. So we're dealing with a random variable, we'll call it x.
Okay.
And it has an expected value, ex, which we often just call e, and a variance, vx, which is squared.
The mean and the variance, the center and the scatter.
Exactly. And crucially, we have to define some positive distance away from the mean. We'll call that a.
And the inequality then states that the probability that the absolute deviation of x from its mean is greater than or equal to that distance a
is less than or equal to the variance of x divided by a squared.
Formally, px, ex, a, nx.
That formula is, it looks deceptively simple, but every single component in there is vital for understanding stability.
So let's break down those two key parts that determine the size of that upper bound, because we want that bound to be small, right? A small bound means a high guarantee of stability.
Right.
So first, the numerator, phi x, the variance.
If the variance is large, it just means the values are highly scattered. Imagine an archer. If their arrows are all over the target, that's high variance.
Makes sense.
So logically, if the scatter is high, the upper bound on the probability of a wild shot, a large deviation, must also be high. High volatility makes it harder to guarantee things will stay close to the average.
So that confirms our basic intuition. Now for the denominator, a squared. This is our chosen distance, but it's squared.
And this is where the magic happens. This term shows us how our certainty improves as we allow for a little more error. If we increase our tolerance interval,
If we say, okay, I can live with a slightly larger deviation,
Then the probability bound shrinks. And crucially, it shrinks quadratically.
that quadratic relationship is maybe the most profound part of the formula.
I think it is. If you, for instance, decide you can live with twice the error distance, so A becomes 2A,
Yeah.
the maximum risk of being outside that new, larger boundary doesn't just get cut in half.
It quarters.
It quarters. Because you're dividing by a squared, which is now 2A or 4A.
So, practically speaking, if you're an engineer trying to minimize the probability of a catastrophic failure, a huge deviation, you don't need to linearly increase your safety margins. You get this accelerating return on precision.
Yes, an accelerating return. If you can move your acceptable error margin just a little bit further out, your security against the absolute worst-case scenario improves exponentially.
Wow.
It's a mathematical gift. It provides the mechanism for this accelerating stability in systems. The farther you look from the mean, the faster the chance of finding something just plummets. Hashtag tag, 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 the paradox of power versus precision.
This brings us to a really interesting tension, though, a sort of paradox in the inequality. We've just established how powerful this bound is, and it applies to any random variable, right?
It holds true for every distribution, discrete, continuous, skewed, uniform, you name it. If you can define a mean and a variance for it, Chebyshev works.
That's the definition of a universal guarantee.
It is. That's its monumental strength. We can use it when we are mathematically, ignorant of the specific shape of the distribution.
And here's the paradox. Because it's so universal, because it has to cover the absolute worst-case scenario for every possible shape of probability distribution.
It often has to give a very high, very conservative, or as the sources put it, a grob or crude estimate.
That's the weakness.
That is the weakness. It's the cost you pay for universality. If we knew the distribution was, say, a perfect bell curve, a normal distribution.
We could use more specialized tools.
Exactly. We could get a much sharper, much lower boundary for the risk. But when you only have the mean and the variance to go on, Chebyshev gives you the absolute floor of certainty. It's the ultimate safe harbor, but it's often, a bit overly pessimistic.
Like an insurance policy against the unknown.
That's a great way to put it.
So if we know our data is well-behaved, we can do better. But if we have no idea, or if we suspect this distribution is just bizarrely shaped, Chebyshev is the only guarantee we have.
And a safe, crude bound is a lot better than no bound at all. And you can flip the logic, which is often more useful in practice, especially in something like quality control.
How so?
Instead of focusing on the maximum risk of being outside the bound, we ask, what is the minimum probability of staying within the bound?
Okay. The inverse.
And that's a simple flip. The probability of x being close to the mean, so within distance a, is greater than or equal to 1 minus vx over a squared.
So it's a guarantee of how much probability mass must be clustered near the center. Okay, now let's get into the proof. This is where it gets really interesting for me. Because this proof, especially for a discrete variable, is just shockingly elegant.
Yeah.
It only relies on the basic definition of variance.
It really is beautiful. We start with the definition of variance for a discrete variable. So Vx is the sum over all possible values xi of the squared deviation from the mean.
Xi minus Ex squared.
Weighted by the probability of that xi. It's the fundamental definition of scatter.
And the genius of the proof is what happens next. It's this key trick. We conceptually split that massive sum into two distinct parts.
Right. We partition the data. We split the sum into, let's call it area A, which covers all the values that are close to the expected value.
Inside our boundary.
And area B, which covers all the outliers. Everything where the deviation is greater than or equal to our chosen distance A.
Okay, so we have our insiders and our outsiders.
And since we are summing up squared terms and positive probabilities, every single component in both area A and area B has to be positive.
Right.
So here's the crucial move. We simply decide to discard the sum over area A. We just throw away the contribution of the inner well-behaved values.
And if we throw away a sum of positive numbers, the total value has to get smaller.
Or stay the same. Which lets us establish the first part of our inequality. The total variance Vx must be greater than or equal to the variance contributed by only the outliers in area B.
Wait, I have to pause on that. If we just discard all the data points close to the mean, aren't we guaranteeing a worse result? Why is that simplification necessary? It feels like we're losing information.
We are. That's exactly right, and that's a fantastic question. We are intentionally making the right side of the inequality smaller. We are throwing away information.
And that's where the crudeness comes from.
That's precisely where the grob nature of the bound comes from. By making this simplification, we ensure the inequality holds for all distributions, because we're no longer relying on the specific shape of the probability function, just the raw definition of variance. We've successfully isolated the variance contribution from only the outliers.
Okay, that makes sense. That's step one. So now step two, we exploit the very definition of area B itself.
For every single data point xi that is in area B, we know by definition that its distance from the mean is at least a.
Okay.
Therefore, its squared deviation, xiex, must be greater than or equal to a squared.
So we do a substitution. We take the variable term, the specific squared distance of each outlier, and we replace it with the constant smaller term, a squared.
We've moved from summing up the actual squared distance of the outliers
Yeah.
to summing up their guaranteed minimum squared distance,
And since a squared is now a constant, we can pull it out in front of the summation sign.
which leaves us with Vx is greater than or equal to a squared times the sum of the probabilities in area B.
And the sum of all the probabilities of the xi's that are in area B, well, that's just the total probability of landing in area B.
Which is Px,
So we have Vx is greater than or equal to a squared times that probability.
Divide both sides by a squared, and you're done. The result is mathematically guaranteed. It just falls right out.
It's remarkable how little information you actually need, just the definitions of mean and variance. That simplicity is why it has such incredible power. As fascinating as the pure math is, when we're applying this in the real-world finance, physics, engineering using an abstract distance A isn't always that practical.
No, you need context. You need to express that deviation relative to the natural measure of scatter in that specific system.
Which is the standard deviation, sigma.
Right. This process makes the measurement dimensionless, which makes it universally comparable. It doesn't matter if you're measuring nanoseconds or light years.
So we do a transformation. We set our deviation distance A to be equal to k times sigma, where k is just the number of standard deviations we're looking away from the mean.
And when we substitute A equals K sigma into the inequality, something really nice happens.
Okay.
We replace Vx with sigma squared, and we replace O squared with K sigma, which is K squared times sigma squared. The sigma squared term, the variance, it just cancels out.
Leaving us with an incredibly elegant, universally cited result. The probability of deviating by more than k standard deviations is at most 1 over k squared.
Px, Ex, sorry.
That is so clean.
It is, because now the actual amount of scatter, sigma, doesn't even matter. All that matters is how many multiples of that scatter C you're willing to tolerate.
And if we focus on the inverse again, the guarantee of stability, the probability that we stay within this k sigma region is at least 1 minus 1 over k squared.
Mm-hmm.
Now, before we run the numbers, let's just touch on that boundary condition again. We said it can be trivial if the bound is 1 or more.
Right. The result 1 over k squared is only informative when k is greater than 1. If k equals 1, the bound is 1 over 1 squared, which is 1.
Telling your boss the risk of something happening is less than 100% is not helpful.
Not helpful at all. This inequality really functions as a restraint on true outliers events that happen beyond the typical immediate scatter of 1 sigma.
Let's look at some concrete examples. This is where the power of the guarantee really sinks in for a practitioner.
Okay, let's take K2. That's a very standard threshold in quality control, in finance. We're asking, what is the absolute minimum percentage of our data that must fall within 2 standard deviations of the mean?
The formula says the probability of staying within 2 sigma is at least 1 minus 1 over 2 squared.
Which is 1 minus 14, so 75%.
And the insight here is enormous. At least 75% of your values have to fall in that 2 sigma range. It doesn't matter if your distribution is skewed, flat, has weird peaks. It's a mathematical floor that holds universally.
If we push it out to K3, which is often used in Six Sigma or high reliability engineering, we get a guaranteed containment of at least 1 minus 19, which is about 88.9%. And at K4, you're guaranteeing almost 94% containment.
And just as a crucial point of comparison, we know that for the very efficient bell curve-shaped normal distribution, about 95% of its values fall within 2 sigma.
And that contrast really highlights the grob nature, the crudeness we talked about. The normal distribution is great at clustering its data. It gets 95% containment.
But Chebyshev's has to account for the weirdos.
It has to account for those theoretical monster distributions that might be incredibly flat or have really thick tails far from the mean. But knowing that the absolute floor is 75% for any process, that gives you profound security, even if it's an overly conservative estimate for most of the data you see in the real world.
Okay, so we've established this universal safety net, but how useful is it really? We saw it can be trivial sometimes. So let's take this inequality out for a road test against a known contained system, the classic EARN model.
A great test case. So we set up the parameters. We have an EARN, 20 balls total, 12 of them are red.
So the probability of drawing a red PHAM is 0.6.
Right, 12 over 20. And we decide to draw 5 times, any 5. Our random variable x is just the number of red balls we draw.
And we're going to test how sharp Chebyshev's bound is by comparing two scenarios that differ in one really crucial experimental step. Scenario A, sampling with replacement. So after every draw, we put the ball back in the urn.
Which refreshes the probability pool. Every draw is independent. This creates a classic binomial distribution.
So first, we need the expected value and variance.
The expected value EX is simple. N times P, so 5 times 0.6, which is 3. We expect, on average, 3 red balls.
And the variance?
The variance, VX, is N times P times Q, where Q is 1 minus P, so 0.4.
So 5 times 0.6 times 0.4, that's 1.2.
VX is 1.2. Okay, now let's set our tolerance. We want to find the probability of a deviation of at least A equals 1.
So we want the max probability of getting 0, 1, 2, or 4, 5 red balls, anything but 3.
We plug our values into Chebyshev. The probability that x3 is greater than or equal to 1 is less than or equal to the variance, 1.2 divided by a squared, which is 1 squared.
So the bound is 1.2.
The bound is 1.2.
That's cute.
And that result is mathematically correct, but it's practically useless, as the sources point out.
Just probability can't be more than 1.
Right. Telling us the maximum risk is 120% provides no actual restraint on the system. In this specific setup, the variance of 1.2 is just too large relative to the small deviation of 1 that we chose.
So the inequality just isn't informative here.
Right. For context, if we actually calculated the exact binomial probability for this, we'd find the chance of getting a deviation of at least 1 is around 65%.
So Chebyshev was correct. 65% is less than 120%, but it offered no real predictive value. Okay. Now, let's change one small thing about the system. Same setup. 20 balls, 12 red, 5 draws, tolerance of 1. But this time, we sample without replacement.
And this switches the statistical structure entirely. We're no longer binomial. We're now dealing with a hypergeometric distribution.
What happens to the expected value?
Interestingly, the expected value, EX, is still 3. The average expectation doesn't change just because we stop putting the balls back.
But the volatility, the variance, has to change. The experiment is fundamentally different. So why does the hypergeometric distribution have a lower variance than the binomial in this case?
This is the crucial physical insight. Think about what's happening in the urn. In the binomial case, every draw is independent. The probability pool never changes.
It's always 0.6.
Always. But in the hypergeometric case, the events are dependent. If your first draw is red, the pool now has fewer red balls.
Making the next draw less likely to be red.
Exactly. If you get a long string of red balls, say 3 or 4 in a row, you have physically depleted the supply of red balls. The system has a self-correction mechanism that actively works against extreme outcomes.
Because the possibilities sort of exhaust themselves.
They do. And because those extreme outcomes become less likely, the entire probability mass pulls itself tighter around the mean. The distribution is damped, the scatter must decrease.
So the variance shrinks.
The variance shrinks. In this case, the variance, which was 1.2 for the binomial, decreases to about 0.95 for the hypergeometric.
And that small change makes all the difference.
It does. We plug the new, smaller variance into Chebyshev's inequality, keeping a 1. The new result is the probability is less than or equal to 0.95 divided by 1 squared.
So less than or equal to 0.95.
A guaranteed upper bound of 95%. Now that is a non-trivial statement. It provides actionable information about the system's stability.
So the lesson here is that the sharpness of Chebyshev's bound is directly proportional to how small the variance is in the system you're analyzing.
We didn't change the inequality. We changed the system to make it inherently less volatile. And suddenly the universal guarantee became much more useful.
Okay, so we have this robust universal tool in Chebyshev's that tells us values tend to cluster around the mean, especially if the variance is small.
Right.
Now, we take that idea and we scale it up exponentially. We move from looking at the scatter of a single experiment to the long-term aggregated stability of repeating that experiment over and over and over.
And this transition leads us to the second, and I would argue most important, concept in this deep dive. The weak law of large numbers, the WLLN.
This is the foundational principle that makes statistical inference even possible.
It's why we trust averages. It's why pollsters sample thousands of people. It's why insurance works.
And we have to give credit here to Jacob Bernoulli back in the 17th century. I mean, you have to pause and reflect on the magnitude of that intellectual leap.
Absolutely.
Yeah.
Before Bernoulli, people understood probability in theory. A coin is 50-50. But there was no mathematical proof that the results you see in the real world must eventually align with that theory.
His challenge was fundamental. How do you connect the observed relative frequency, what we measure, h sub n, to the theoretical abstract probability, p?
And the WLLN is that mathematical bridge. It provides the essential guarantee. When an experiment is repeated often enough, when it gets large enough, the measured relative frequency must stabilize and approach the true probability.
The intuition is just so clear. Chaos in the short term, order in the long term. If I flip a coin 10 times and get 7 heads, that's 70%. It's noisy, but I'm not that surprised. But if I flip it 10,000 times and I still get 70% heads, well, now I'm thinking the coin is rigged. The noise should have averaged out.
That averaging out process, that dampening of random chance through repetition, is exactly what the WLLN formalizes. It is the law of statistical gravity. It ensures that your measured results are pulled relentlessly toward the true theoretical value. Hashtag 3.2 mathematical formulation and interpretation. So let's look at the actual mathematical formulation. We've got an event with probability p. We repeat the experiment n times, and hn is the relative frequency, the number of hits divided by n.
Okay. And the core of the theorem is expressed as a limit. We look at the probability that the distance between our measured frequency hn and the true probability p is less than some tiny predefined tolerance. We'll call it epsilon.
And the limit states that as the number of trials approaches infinity, this probability tends toward 1.
In layman's terms, you pick a tiny sliver of error. So say 0.01.
Right.
The WLLN guarantees that if you repeat the experiment enough times, if you increase it enough, the probability that your measured frequency is outside that tiny error margin shrinks relentlessly towards 0.
The certainty that your measured value is close to the true value tends toward 100%.
And this is a key distinction we have to make. The WLLN doesn't say that a large deviation becomes impossible.
No, absolutely not.
It just says it becomes extremely, vanishingly unlikely. This is what's called convergence in probability.
Random chance isn't eliminated. It's just tamed and averaged out by sheer repetition.
We can visualize this really well with the dice roll example. Let's say the true probability of rolling a 6 is p equals 16, so about 0.167.
Okay, if you simulate, say, n50 throws, your results are going to be noisy. The relative frequency histogram will be broad and scattered. You might see 10% sixes. You might see 25%. It's wide.
But now you increase the experiment size to n at 200.
The distribution has dramatically pulled itself inward. The scatter is reduced. And the probability mass is now concentrated much more strongly around that true value of 0.167. The curve is narrower and taller.
And the WLLN guarantees that as n continues to infinity, a million trials, a billion, that distribution doesn't just get narrower. The probability mass concentrates so completely that the peak effectively collapses into a single, infinitely sharp vertical line right at the true probability p.
And that mathematical concentration of certainty is the fundamental reason why large samples are trustworthy.
Okay, now for the synthesis. We have the law of large numbers, which is our goal. And we have Chebyshev's inequality, our universal robust tool. The elegance here is that we can prove the existence of this long-term order using only the guarantee we have against short-term scatter. Hashtag 4.1, setting up the binomial framework.
Right. So we first have to frame the process in terms of Bernoulli trials, success-failure experiments, like the coin flip.
Or the EARN model with replacement.
Exactly. We start with the absolute frequency, x sub n. That's the total number of successes in trials. Since it's a chain of independent trials, xn follows a binomial distribution.
And we know its parameters. The expected number of successes, exn, is n times p, and the variance, vxn, is n times p times 1p.
But the WLLN is about the relative frequency. So we have to analyze the behavior of h sub n, which is just the absolute frequency divided by the total number of trials. hn equals xn over n.
And we need the expected value and variance of this new variable, hn, because those are the two things we need to plug into Chebyshev's inequality. Hashtag 4.2, the crucial calculations. Okay, let's start with the expected value of the relative frequency, an.
So because the expected value operator is linear, we can just pull that constant, 1n, out front.
So ahn is exnn, which becomes 1n times exn.
And we already know that exn is n times p, so we substitute that in, we get 1n times p.
The n's cancel.
And we're left with exactly p.
And that is a beautiful, crucial result that confirms our intuition. The expected value of the relative frequency is the true probability. The sources call this Erwartungsstö, an unbiased estimator.
It means, on average, your measurement process will hit the true target exactly.
Okay, now for the variance, VHN. This is the algebraic centerpiece of the entire proof.
It really is. When we factor out that constant, 1n, from the variance, we have to remember the crucial variance rule.
You have to square it.
You have to square it.
Yeah.
So VHN equals VXN. We pull out 1n squared. So we have 1nn times VXN.
And now we substitute what we know for VXN.
Which is NP1P. So the expression becomes 1n times NP, 1p. One of the n's in the denominator cancels with the n in the numerator,
leaving us with the final defining expression for the variance of the relative frequency, p times 1p, all divided by n.
And that is the key takeaway. That is the entire engine that drives statistical stability. The variance of the relative frequency is inversely proportional to n.
Because we divide by n twice, really, once for the definition of relative frequency and a second time because the variance operator squares the constant.
That 1n relationship is the mathematical proof of long-term order. As n increases, the scatter of the relative frequency doesn't just get smaller, it actively collapses towards zero.
It's like statistical dampener.
It is. If you double the number of trials, you have the variance. If you multiply the trials by 10, the scatter shrinks to 1/10 of its original size. Share 4.3, the convergence moment.
So now we have everything we need. We take our universal guarantee, Chebyshev, and we plug in the known behavior of the relative frequency.
Its expectation is p, and its variance is p1p over n, and our deviation threshold is that tiny number, epsilon.
So the inequality now states that the probability of our relative frequency deviating from the true probability by epsilon or more is bounded
by the variance of HN divided by epsilon squared, which is epsilon $3, epsilon $2 beta.
And now, the moment of truth. Look closely at the right side of that equation. That's the upper bound on the risk of a deviation.
The numerator, P1P, is some fixed number. The tolerance, epsilon squared, is also a fixed number we chose. The crucial element is n, the number of trials sitting there in the denominator.
And as we let n approach infinity, as we run more and more and more experiments,
the denominator grows infinitely large, which forces the entire fraction to shrink towards zero.
Conclusion. The upper bound on the probability of a deviation tends toward zero.
QED. The weak law of large numbers is proven. It's just a stunning realization. The combination of Chebyshev's robust bound and the simple algebraic consequence of calculating the variance of a relative frequency. It mathematically enforces the stability of long-term randomness.
It's incredible. The genius of Bernoulli, proven by Chebyshev, is that by simply dividing the outcome by the number of trials, you introduce that 1n decay factor into the variance, which forces the whole system to converge to certainty. The proof is elegant, but let's bring it back down to the applied side. If you're an engineer or a data scientist trying to design an experiment, you face what the sources call a hen problem, a chicken and egg problem.
Precisely. To calculate the required sample size, using that full formula, you would need to know the true probability, p.
But you're running the experiment to find p in the first place. You can't know it before you start.
So we need a way to make that bounding formula independent of p so we can pre-calculate how many trials we need. We have to identify the worst-case scenario that maximizes the risk in the numerator.
Which is that term, p times 1p.
And that function fp, ep, is maximized when a p is 0.5.
A 50-50 coin flip.
Exactly. That experiment is maximally uncertain, maximally volatile. Any other value of p, like 0.1 or 0.9, is less volatile because you're naturally biased toward one result.
So at p.5, the maximum value of that numerator is 0.5 times 0.5, which is 0.25, or 1/4.
And this is the genius move for practitioners. You replace the unknown p1p with its absolute maximum possible value, 14.
Which guarantees your upper bound is safe and conservative, no matter what the true probability p actually is.
You're assuming the highest possible level of volatility for the system you're about to measure.
And the resulting gold standard formula is independent of p. The probability of a deviation is less than or equal to 1 over 4 times n times epsilon squared.
And that formula is invaluable because it's the definition of statistical planning. If you're an engineer and you need your measured failure rate to be estimated to within, say, epsilon equals 1% accuracy.
And you want a guaranteed maximum failure risk on that estimation of, say, 5%.
You can solve for n.
So if we set that bound at 0.05 and our required precision epsilon at 0.01.
We rearrange the formula to solve for n.
Yeah.
And n has to be greater than or equal to 1 divided by 4 times 0.05 times 0.01 squared.
Which comes out to
You would need n to be greater than or equal to 50,000 trials.
50,000 trials, just to guarantee that our measured frequency is within 1% of the true value with 95% certainty. Number is large, but the security is absolute.
Because we use the worst-case scenario. It demonstrates the deep mathematical cost of achieving statistical certainty when you don't know the underlying volatility. And this final formula, it's the ultimate takeaway. It moves statistics from a philosophy of chance to a discipline of prediction. It lets us quantify exactly how much effort is required to achieve a desired level of accuracy, epsilon, with a known maximum risk. #tag outro.
That was an incredible, detailed journey. We started with the simple, robust, universal safety net that Chebyshev's inequality provides.
A mathematical guarantee that works even when we know almost nothing about the system except its mean and variance.
We established that its power comes from its simplicity, but its drawback is its crudeness, its conservatism, because it has to account for every possible distribution shape.
We then use the power of that bound, combined with the provable fact that the variance of relative frequencies shrinks inversely with the number of trials, that 1n factor,
A direct consequence of dividing by n twice.
to mathematically prove the weak law of large numbers.
And the grand synthesis is just crystal clear. Random events are chaotic in the short term, but they're stable in the long term. The measured relative frequencies must converge to the theoretical probabilities.
It's not just an observation, it's a mathematical necessity enforced by algebraic reality.
And this convergence is the absolute mathematical cornerstone of all statistical inference. It is the sole reason we can rely on averages, why we trust large sample sizes in science, why the entire multi-trillion-dollar insurance industry can calculate risk and remain profitable.
Without the WLLN, which is derived ultimately from the bounding power of Chebyshev, statistics as a predictive discipline would simply not exist.
Now, a final thought for you to chew on. We proved the weak law of large numbers. That guarantees convergence in probability, meaning large deviations become improbable. But is that enough for high-stakes decisions? Or must we know that large deviations are mathematically impossible over the long run?
And that philosophical and technical distinction is the difference between the weak law and the strong law of large numbers.
And while the relative frequency converges to p, the absolute count of successes, xn, continues to scatter. As n goes to infinity, that scattering distribution doesn't just get wider, it takes on a specific, powerful, and universally applicable shape.
A question that leads us directly into our next great topic, the central limit theorem.
That's a deep dive for another day. Until then, stay curious.